All right, this is week 11. We're going to be talking about the small step chapter. Small step semantics is the topic. So let's just start off with a bit of an overview of what this really means. In the previous chapters, we've talked about evaluation for the IMP language, and one of the ways we've defined it have typically been what's known as a big step style. In other words, you have a program and you want to know what the answer is at the end. So you think of it as making a big evaluation step all the way to the final answer. So for expressions, that might be taking a complex expression and the answer is the value of the expression. Or similarly for a command, you're given an initial state, you evaluate to the end to get the final state. And this is useful, as we've seen, but it's not the only way to think about things. Often what you want to do is be able to reason about and discuss the intermediate parts of the evaluation. In other words, what happens along the way to the final answer. So this alternative style is often called small step. So in the small step style, what you're interested in is making the sort of smallest step you can to progress the evaluation, and a full evaluation is just composed of a sequence of these small steps. So that's the point of this chapter. The two approaches have advantages and disadvantages depending on what you want to do. So if you're only interested in the final answer, then you might as well just use a big step semantics because you don't really care about what happens along the way. However, in some applications, and the example they give here is concurrency, where you need to be thinking sort of, say you've got a language where you're modeling concurrent threads, you need to be able to reason about how those threads interact with each other along the way, and it might be non-deterministic, so it may not be an obvious evaluation where they all step at the same time, for example. So we're not going to do that really in this course, but the motivation is there. This second shortcoming here is interesting for what we're doing. So the issue is basically that in a big step style, we're basically saying we have to be able to get to a final state, otherwise the evaluation just isn't defined. And it might be the case that we can make some progress to that evaluation, but we get to a position in the middle somewhere where we can't do something. So the example in the chapter here is that they consider, well, maybe we have two different sorts of data types, numbers and lists of numbers, and it's possible to write a program that sort of doesn't really make sense, like adding 2 to nil. And when you get to the point of evaluation, you in a big step semantics, it's sort of hard to say what that really means. So you could hack it in and say, well, lists are equivalent to 0 or something, which is what they say here, but that, as they say, that's a bit of a hack. So a more sort of natural way is to say, well, this operation 2 plus nil is just undefined, so there's no way to evaluate that to a result at all. And as we saw in the previous chapters, we can model that kind of situation by using relational definitions for things instead of functional ones, the fixed point versions. So essentially they're partial functions. So we could say this expression, if it evaluates correctly, will evaluate to a certain value, or it might not have a map to any value in the case that it's undefined. But the problem with that is that we now have a situation where when we talk about a big step evaluation, if that's not defined, it might be for two different sorts of reasons. So one might be something like an infinite loop where we never get to a final state. And the other one might be that along the way we get to a position that doesn't make any sense, so we can't get to a final state because the program is just nonsensical for some reason. And from the point of view of big step semantics, they're sort of indistinguishable situations because it's just there is no final state that we can get to. Whereas with small step, as we'll see in this chapter, we can reason about evaluations that go for a while and then get stuck. In other words, there's no way to make any more steps from some position, and evaluations that just go on forever. In other words, keep making steps but essentially make no progress, so as would be the case in an infinite loop. So this is one reason for preferring a small step thing. You can distinguish between these two situations. Okay, one thing you may be wondering is, in this sort of case with a 2 plus nil, why would we ever try and evaluate that program? Because it's not well typed. We're still in the world in this part of the course where we're not considering types really. A good chunk of the rest of this book is about type systems, and essentially you can think of type systems as sort of cutting down the legal programs that the evaluation has to worry about. So in that sense, the 2 plus nil program would be rejected probably by a type system, and then the evaluator wouldn't have to worry about the meaning of that. But in this context, we're still wanting to sort of think about these sorts of things. Okay, so in this beginning part, just to motivate or just to illustrate this idea, they step backwards from imp to a much simpler language. So it's this TM language for terms. And there's just two constructs. There's constants, which are natural numbers, and pluses, which take two terms and give you a term. So it's just a subset of the arithmetic expressions, really, of the imp language. And so this is the sort of standard functional definition of the evaluator. So we can take a term and give a natural number, and that's obviously a simple recursive definition. We can also define that as a big step relation, where a term t is related to a number n if, and that means t evaluates to n. In other words, if you go evaluate all the way to the end, you get n when you start with t. So for example, a constant turns into the number, and a plus recursively evaluates the two pieces, and then the thing that the plus is related to is just the sum of the two sub-expression values. So this is very similar to what we've seen before with A-eval and A-eval R and also that sort of stuff for the imp language. And we can define that with a simple relational version that encodes these inference rules. So that's pretty simple. So what would this look like in a small step style? So small step, you should think in terms of, I've got a term, in this case just ones with constants and pluses in it. And what I want to do is evaluate some piece in a sort of minimal way to make some progress towards evaluating the whole thing. So in this notation down here, the double equals arrow here, it means making a small step, not stepping all the way to the end, but just making one evaluation step. So there's three rules here. I actually think this one is the best one to look at first. So this is saying that if I've got a plus with two terms in it, and the left term can make a step to some other term, t1 prime, then the whole thing makes a step to p t1 prime t2. So the t2 doesn't change, but the t1 is evaluated a little bit. Okay, And this only applies if T1 can be evaluated a little bit. Okay, so if it's a constant, for example, we can't evaluate constants anymore, so there won't be any rules for constants. So if the left argument is already a constant, this won't apply. So in the second case, we can say, well, if we already know that the first part of the plus is a constant, then we can try and step the second part, which is this condition here. So if that's possible, then we can step the whole thing by just updating the second component. And if we're in a position where both pieces of a plus are constants, then we apply this rule at the top here, which basically says we can step a plus of two constants into a constant of the sum of the two constants. And if you think about it for a bit, this is enough to cover all the evaluations that we might want for this simple language. So if we have a constant, we can't step at all, so that we're done. If we have a plus, then we can apply one of these three rules. If we can step the components, we try the left one first or the right one. Notice that this implies, these two rules together imply that we always evaluate the left component of a plus before we evaluate the right component of a plus. And once they're both evaluated, we can evaluate to the final constant. And this is fairly easy to encode in the normal way that we've been using as an inductive relation. We call it step. So it's a relation between terms, and it just expresses exactly the inference rules that we had up the top there. Okay, so this is just a bit of explanation that we've already done. So you can sort of see it in operation here, that if we have a nested set of pluses like this, then if we do one step, remember this is just a single step, then all that changes is this left piece of the plus turns into a constant of the sum, right? So all we're doing is applying the plus one rule at the top level and then the plus const rule at the next level. So we can have a look. So this over here is the full thing. So when we apply the st plus 1, we now have to do a step for the left component of the top level plus, and we can do that by using the st plus const rule. And the same sort of thing applies for this one. So in this one, it's a plus of a constant, with the right-hand side of that plus being another plus of a constant, with the right-hand side of that being a plus of two constants. So we have to, if we're trying to evaluate this one, we have to apply, we can't apply plus const because we've got a constant and a plus as the two children here. We can't apply plus 1 because the left-hand child is a constant, so it's not going to be able to step. So we have to apply plus 2. Right, so if we make it a bit more visible. Okay, so this is the top of the plus 2, if you like. So now we have to be able to show that the right-hand side of the original thing can step. And again, we've got a constant here and a plus, so we can't, the only rule we can use is plus 2 again. Okay, and now we're doing the right-hand side of the right-hand side, and we can apply the st plus const rule to do that one. Okay, so this is a fairly simple process for this language, but you can generalize this, as we'll see at the end of the class this week. We'll see how to do a lot of this for the imp language. This is enough for this simple language. Okay, we'll stop there and we'll come back with some more general discussion of relations in the next part.